What are particles? And in this presentation, we're discussing subatomic particles, right, which are smaller than the atom. And just to be clear, particles in this reference do not refer to macroscopic matter, things that can actually be seen. We're talking about, such as dust. We're talking about things that are smaller than the atom. So hereafter, particles refers to subatomic particles. Okay, now that that's out of the way, let's get to what that means. And we're going to start with the atom. Because inside everything, all of matter, are molecules, right, which are made of atoms, and there are components of these atoms, 3 of them. Right, the electron was discovered first in 1897, and then in the nucleus of the atom, the proton was discovered around 1920, and the neutron in 1932. 3 subatomic particles that make up the atom. And even before the discovery of subatomic particles, atomic elements started to show a relationship. It started with this man. In 1869, Mendeleev published the first version of the periodic table of elements. You've likely studied that in chemistry class, and it looks like this. The periodic table of elements organizes the 118 known atomic elements, beginning with hydrogen, and it's based on the number of protons in each atom. And you can see the proton count circled here. It's in the top left. Right? Hydrogen has 1. You can see that circle move over to helium, has 2. Lithium has 3, and so on. That's the table. So we know that all of matter is made of atoms, right? And atoms consist of these subatomic particles. But the key particle is the proton, because it determines the atomic element. Here you have lithium again, 3 protons in the middle, fluorine, 9, aluminum, 13, and it's really based on protons. You know, electrons will try to match the proton count to be stable, but an atom can be ionized. Lithium could lose a couple of electrons and it's still lithium. So the proton is the key particle. And the table was built based on a linear relationship between the proton count, i.e. the atomic number, and its weight, i.e. the atomic mass. And you can see the graph on the left, and that's the linear relationship. And what that allows chemists to do is to be able to predict, you know, brand new atomic elements, ones that haven't been discovered yet. They knew exactly what the weight would be and where it would be. Right? And it's simply based on a missing proton count from 1 to 118. Now that's atoms, so let's move on to particles now. Now by the first half of the 1900s, 3 subatomic particles were known. Just to recap, these are the components of the atom: the electron, the proton, and the neutron. And thanks to the Particle Zoo for these images of all the particles that we're going to see. Now, by 1930, another particle was theorized, and then it was finally discovered in 1956. And that's the neutrino. And to date, it remains the smallest and lightest particle discovered. And these are incredibly small. Right? The mass of the neutrino is really a range that hasn't been finalized yet, but you know, we're talking about a couple 100,000 neutrinos to equal the weight of an electron. An electron is incredibly small itself. So the neutrino is a very, very small particle. And its low energy, I mean its low weight, makes it really difficult to find. And there's really these elaborate experiments that have been built to detect them, you know, deep underground in mountains, in wells, and these neutrino detectors eventually are able to spot, out of the billions and billions of neutrinos passing through the Earth, 1 or 2, if they're lucky. That's how it works, to find neutrinos. And after these neutrino detectors were built, it's interesting because 2 more neutrinos have been discovered. And they have names like muon neutrino, and tau neutrino. They are larger, but yet interestingly, as neutrinos, which are produced by the sun and travel to Earth, as they travel, they can transform from one particle to the next. A neutrino can become a muon neutrino or a tau, mysteriously. Now, meanwhile, there's another type of experiment, right, that smashes particles at high energies to determine its components. particle accelerators. And in 1968, protons were smashed together and two types of quarks were discovered. A proton really has three different quarks, two up quarks and one down quark. And neutrons similarly also have three quarks, but they're also these two components, up quark and down quark. So now we have more particles that have been discovered, again, that are smaller than the atom, in this case components of the proton. And in the past half century since, dozens more of particles, unique particles, have been found using this method, smashing particles together to see what are their components. And really it's a zoo. It's a mess of particles, and perhaps one of the most famous particles recently that was discovered is the Higgs, found in 2012 using this method. So new subatomic particles continue to be discovered, but most are traced back to what are known as elementary particles. And so similar to the periodic table of elements for atoms, physicists try to do the same thing with subatomic particles. And this is the standard model of elementary particles. See a couple of the quarks that were mentioned there and the neutrinos which we covered. And there's more, which I won't cover today. And there's 17 elementary particles in the standard model to describe roughly about 200 particles that have been discovered so far. I know the standard model in this picture has 18, and that's because one of the particles, the graviton, is undiscovered, is theoretical. So there's 17 at the moment for the standard model. But here's a question, right? Could nature be simpler than what it seems? So recall that 118 different atomic elements, were eventually determined in the last century to be based on a combination of protons. Simply this, the proton. And it's the proton count that determines the elements. And again, just to recap, it was based on this linear relationship between the proton count and the atomic mass. So here, this very, very interesting thing now where a similar linear relationship exists with subatomic particles between particle count, right, that's equivalent of proton count, and energy, equivalent of atomic mass. And here again, we see a unique trend that's a linear relationship, but this time around it's not as obvious, right? It's not linear naturally. You need to take the particle count to the 5th power, and you need to determine a baseline particle. And the details are published in a paper. You can find the URL below. But that baseline particle, so this relationship is possible when considering a baseline particle, otherwise considered a fundamental particle. And it, just like proton creating all the different elements, if you assume a fundamental particle model, then we can assume, just like how protons build atoms, perhaps a fundamental particle could build all other particles. It's a theory, but it's worth exploring. All right, but the question is, all right, a fundamental particle in this model requires something around 2.39 eV. eV is electron volts. All right, so what particle, if it is a fundamental particle, is near this energy value? Well, interestingly, the neutrino happens to be in that range. It also happens to be the smallest known particle that we have found so far. Again, worth exploring, a very different model for particles. But as Leonardo da Vinci once said, simplicity is the ultimate sophistication. Thank you.